Hello everyone, this is Mr. Chang. So I'm sorry that not here today, but I have pre-recorded this lesson so that you can follow through. I will also put the link up on our course webpage for the video. If you need to go home and rewatch it, you could. Now today we're going to talk about surface friction. So the friction when, let's say, you have two objects, one on top of each other, and you try to push one of them, and you feel a friction trying to oppose your movement. Okay, so now let's say you have a box sitting on a table, which is like this picture you see right now. Now it might look like the surfaces are really smooth, but if you actually, let's say, have a microscope and look at it really closely, you see that any surfaces are actually not as smooth as you think. Now, if you remember, we talked about this like a long time ago, that the surface of an object is basically just the electrons on the outermost shell of the outermost layer of atoms, right? So these are all like electrons that are, well, repelling each other. That's why they can never actually touch. The two surfaces can never really be touched. So what happens when you have these mountain and bodies, these imperfection points on the surface? Well, so what happened is, let's say you try to push one object to one direction. So let's say you try to push the box, which is on top, to the right hand side. Well, then you can see those electrons are going to be preventing you from doing that, right? So they're going to be trying to oppose each other and try to prevent you from moving to the right hand side. So there will be a force which we call surface friction that points to the left hand side. Okay, now let's sum that up into a sentence or two. Friction. So surface friction is created whenever two surfaces move past one another. Okay, so move past each other. Okay, now on the microscopic level, we are looking at irregularity in the two surfaces. So that what they would do is, so because you have these irregularity, they will catch on to each other, and well, in terms, provide like a frictional force to slow you down. Now, one very interesting question, because we talk about the electron and electron of the two surfaces repelling each other. So now it makes sense that the closer they get, right? The closer the gap is in between them, the more friction will become. And so because of that, we can actually see the effect in the equation itself. So let's look at the equation. The equation is very simple actually. So the equation depends on two things. So force of friction depends on mu Fn. Now, so this character, which is a Greek letter, mu. Okay, so let's talk about that in here first. So this character is called mu. So that is called the coefficient of friction. So coefficient of friction. Okay, so coefficient of friction. Now, that is a number. It has no unit. So this is a number that is measured. So for example, any two pairs of surfaces rubbing against each other is going to have a different coefficient of friction. For example, you can have a wooden table and you can put a plastic box on top. So now you have a surface between plastic and wood. Now when you try to push that plastic box on top of that table, friction, you feel friction. And the amount of friction that you will feel depends on these value called coefficient of friction. You can also have, let's say another surface, you can put your hand on your phone, and then it will be the surface between your hand and your phone, and that will have another number called coefficient of friction for that surface already. So therefore, there are actually many different coefficient of friction number depending on what surfaces are you working on. So once again, that symbol has a Greek name. So this is Greek letter, and we call it mu. Okay, MYU, mu, MYU, mu. Okay, someone from my day one class comment that it sounds like the Pokemon meow, but it's actually mu. Okay, so and it depends. So that value depends on the surfaces. Now, typically, what kind of number should you expect? Well, the coefficient of friction is typically between 0 and 1. So, for example, if something is truly frictionless, it will be a 0. And for example, if you have ice frictions on ice, let's say you have two pieces of ice and they're rubbing against each other, ice has a pretty low coefficient of friction, maybe like 0.1, less than that. And or if you talk about, let's say your tire on a car rubbing against concrete on the ground, that would usually be about zero point 0.5 or zero point 0.6, right? Have a mu of about that. Now, what about Fn? So friction depends on, okay, number one is the mu, number two is Fn. So what is the Fn? Well, Fn is our very familiar normal force from the past few classes, right? So that's the normal force. Okay, so remember, it's the normal force, and someone asked me, I think two classes before, is it always equal to gravity? And the answer is not, right? But it is, however, always perpendicular to the surface. Okay, so it's always perpendicular to the surface that you're sitting on. So if you look at the unit for this, force of friction is in Newton. Normal force is also in Newton. Okay, and mu has no unit. All right, now moving on. Okay, so we are going to distinguish between two different types of friction. Now, friction can be either static or kinetic. So static friction is the friction force on a stationary object. So on a stationary object. Now, stationary means that it is not moving. So, for example, if an object is truly at rest. Okay, so let's say an object is at rest. That means it is at this moment not moving. And let's say you're trying to push it. So here's you trying to push the box to the right hand side. Now, in order to make that happen, in order to actually be successful in pushing that box to the right hand side, you need to overcome friction. Well, what kind of friction? You need to overcome something called static friction. Okay, so friction, and let's see, let me put the subscript S on it, so static friction. You need to overcome static friction in order to push this box. Now, so for any object that is sitting on the ground just not moving right now, if you try to push it, you have to be strong enough to overcome the static friction. Now remember, the static friction, if you look at the equation again, depends on Fn. Now in this case, Fn depends on